In acknowledgement of his uncommon commitments to the field of material science, Kaku has drawn broad attention for emphasizing the progressive capabilities of the James Webb Space Telescope, JWST. This telescope has achieved notable discoveries, including the identification of 6 massive galaxies that challenge existing scientific knowledge. These galaxies, once thought to be beyond the reach of scientific study, present a unique opportunity to expand our understanding of the universe. While the significance of these discoveries is intriguing, they also subtly challenge established theories about galaxy formation and evolution. It is essential to assess these findings carefully, as they highlight the crucial role of scientific progress. Kaku, a key figure in the scientific community, is well known for his expertise in both classical physics and quantum mechanics. His unique background, shaped by both American and Japanese cultures, has made him a vocal advocate for exploring the new frontiers unveiled by the JWST. He passionately supports the telescope's findings, sharing them with the public and demonstrating his enthusiasm for expanding our knowledge of the universe. His willingness to engage openly with these new discoveries, which can no longer be ignored, reflects his commitment to advancing human understanding. Kaku's distinctive and compelling perspective stands out in his reflections on the JWST revelations, which have reignited his passion for scientific advancement. Throughout his career, he has been known for his openness to unconventional ideas, welcoming concepts that challenge established paradigms. While he acknowledges that Einstein's theory of relativity and Newton's laws form the backbone of much of modern science, he also recognizes their limitations in fully explaining the universe's complexities. Kaku suggests that the discoveries made by the JWST could potentially revolutionize cosmology, despite the fact that many of his colleagues remain hesitant to accept this view. This skepticism has sparked questions and criticism, particularly among supporters of the Big Bang theory and quantum mechanics. Nevertheless, Kaku remains steadfast in his belief that the JWST has uncovered 6 enormous galaxies dating back to the early universe. Each of these galaxies contains more stars than our Milky Way, despite having formed just a short time after the Big Bang. A group of cosmologists has aptly named these extraordinary galaxies universe breakers because their discovery challenges our current understanding of the universe. If confirmed, these findings would drastically alter our perception of the early universe, demonstrating that its initial stages were far more dynamic and complex than previously thought. The prevailing theory about the universe's origins suggests that after the Big Bang, the universe was chaotic, with the first massive objects taking a significant amount of time to emerge. It was believed that galaxies began forming much later. However, the recently discovered massive galaxies are already larger than the Milky Way, with their exceptional brightness indicating that they may have been forming stars at a rapid rate. In contrast, our universe forms stars more gradually and unpredictably. The exact timeline of the first cosmic structures remains uncertain, but it is clear that the universe may have initially consisted of isolated stars or small star clusters that later merged to form larger groups. For a long time, it was assumed that such enormous and advanced galaxies could not have existed so soon after the Big Bang. This raises a crucial question. Is the universe older than previously believed, or did these massive galaxies form sooner than expected? This idea presents a significant challenge to conventional science, which still struggles to reconcile these revelations with established models. Certain areas of physics have outright dismissed these new findings, questioning the accuracy of age estimates. However, Kaku is aware of these criticisms and has openly expressed his views on this issue. He points out that many outdated theories persist due to the influence of prominent scientists, even though these ideas have already been disproven by more recent research. Kaku emphasizes that true progress in science comes from empirical research that prioritizes the development of rigorous and accurate theories. He also highlights that our understanding of the universe's origins remains extremely limited, underscoring the importance of continuous testing, revision, and refinement in the scientific process. The concept of the universe's origins was first proposed in 1927 when scientists observed that the universe was expanding, suggesting it began from an infinitely dense point and has been expanding ever since. At the time, the idea of a universe with both a beginning and an end was difficult to comprehend for many. Even today, scientists continue to grapple with fully understanding this concept. Nevertheless, it is crucial to remain open-minded about such possibilities, even when new discoveries seem to challenge long-held scientific consensus. History has shown that scientific knowledge is frequently revised. For instance, when Einstein was young, it was widely believed that stars and planets were fixed in space. Today, we know that everything in the universe is in motion. Planets orbit stars, stars move through galaxies at incredible speeds, and galaxies themselves travel through space, their ultimate fate remaining uncertain. This realization challenges long-standing beliefs and underscores the necessity for continuous scientific inquiry and adaptation. Today, scientists are compelled to reconsider anomalies and acknowledge that theories are incomplete until they are rigorously tested and confirmed through observational data. The Big Bang Theory, for example, emerged from observations showing that galaxies were moving apart, with their distances increasing relative to their separation from Earth. This theory, known as Hubble's law, was further validated by evidence such as the cosmic microwave background radiation and the redshift of distant galaxies. However, it is essential to remember that at one point, people believed the Earth was flat and that the Sun revolved around it, beliefs based on the best available evidence at the time. Technological advances have since revolutionized our understanding of the universe. We now find ourselves in a similar position, as new data from the JWST contradicts certain previous assumptions, demonstrating that science is constantly evolving. Experts must remain open to new discoveries while re-evaluating established theories in light of emerging evidence. The astonishing discoveries from the JWST challenge current understanding and prompt a reassessment of long-standing cosmological models. Scientists rely heavily on redshift measurements to determine the distances and velocities of celestial bodies. Redshift refers to the shift in the color of light when light sources and observers move relative to one another. For example, when a distant light source, like a star, moves away from us, its light shifts toward the red end of the spectrum. Conversely, if it moves closer, the light shifts toward the blue end. This phenomenon provides crucial data about the motion and distance of galaxies. It is important to recognize that even minor errors in redshift measurements can have significant consequences. As a result, many traditional evaluation methods are now being questioned due to the new findings made by the JWST. As research progresses, the JWST's discoveries may prompt scientists to reconsider fundamental aspects of cosmology, including the nature of dark matter, dark energy, and the mechanisms that drive galaxy formation. The existence of these massive, early galaxies suggests that our models of how matter clumps together in the early universe may need refinement. If galaxies were able to grow so quickly after the Big Bang, it raises questions about whether our current understanding of gravity, particle physics, and cosmic evolution is incomplete. One possibility being explored is that there were alternative pathways for rapid galaxy growth in the early universe. Perhaps unknown physical processes, such as new forms of dark matter interactions or variations in how gas coalesces into stars, played a role in the unexpectedly rapid development of these structures. Alternatively, scientists may need to revisit assumptions about the cosmic timeline itself. Could the universe be older than currently estimated, or are we missing key details about the conditions that allowed galaxies to form so quickly? The JWST's observations are not only revolutionizing our view of the early universe, but are also shedding light on exoplanetary systems, stellar nurseries, and the chemistry of distant galaxies. By analyzing the light spectra of exoplanets, the JWST can detect the presence of water, carbon dioxide, methane, and other molecules that may provide clues about the potential for life beyond Earth. This capability brings us closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? Furthermore, the telescope's ability to study distant star-forming regions allows astronomers to witness the birth and evolution of stars in unprecedented detail. Understanding these processes is crucial because the life cycles of stars dictate the formation of planetary systems, the distribution of elements necessary for life, and even the long-term fate of galaxies. As groundbreaking as these discoveries are, they also highlight the limitations of even our most advanced technology. While the JWST has pushed the boundaries of observation, it cannot answer every question alone. Future space telescopes, such as the proposed Nancy Grace Roman Space Telescope and next-generation ground-based observatories, will complement the JWST's findings, offering broader perspectives on cosmic phenomena. The next steps in cosmic research will involve refining theoretical models to align with new observational data. Scientists will need to develop improved simulations that incorporate the latest JWST findings to better predict how galaxies evolve, how dark matter influences cosmic structures, and how black holes shape their surroundings. This iterative process, where discoveries challenge existing theories and lead to new models, demonstrates the self-correcting nature of science. Beyond its immediate scientific impact, the JWST's success serves as an inspiration for future generations of researchers, engineers, and space explorers. It is a testament to human ingenuity, perseverance, and our collective quest to understand the universe. Just as the Hubble Space Telescope transformed our view of the cosmos in the late 20th century, the JWST is now shaping our understanding in the 21st century, paving the way for discoveries yet to come. In the coming years, as the JWST continues to observe the universe's most distant and ancient regions, its findings will likely lead to even more paradigm-shifting revelations. Whether confirming existing theories, modifying them, or completely rewriting our understanding of the cosmos, one thing is clear. We are entering a new era of astrophysical discovery, one that will redefine what we know about our place in the universe. As humanity stands on the brink of these extraordinary discoveries, one can only wonder, what other cosmic mysteries are waiting to be uncovered? The journey has just begun, and with each new revelation, we take another step toward unraveling the deepest secrets of existence. Appreciated, and we anticipate seeing you again soon. This call to activity urges watchers to engage with the content, encouraging a community of curious personalities anxious to explore and understand the latest scientific advancements. The ongoing investigation of our universe, with its immense distances and perplexing designs, continues to bewilder and challenge researchers worldwide. From early cosmological hypotheses to the latest breakthroughs, empowered by state-of-the-art technology, each new discovery reshapes our understanding and pushes the limits of human knowledge. One of the core questions in cosmology concerns the origins and development of galaxies. Immense assortments of stars, gas, dust, and dark matter bound together by gravity. Grasping how galaxies structure and develop is vital for unlocking the mysteries of the universe and testing established scientific theories. For instance, the Big Bang Theory, proposed almost 100 years ago, suggests that the universe began as an incredibly dense point and has been expanding ever since. This idea arose from observations of the expanding universe and the cosmic microwave background radiation, the leftover energy and light from the early universe. However, later discoveries, especially those made by the JWST, have raised some skepticism about specific aspects of the Big Bang Theory. With its unparalleled sensitivity, the JWST has identified galaxies that appear to be far larger and more developed than anticipated for their age. One such discovery includes 6 massive galaxies that formed between 200 and 700 million years after the Big Bang, an extremely brief period in the universe's 13.8 billion-year history. These galaxies, referred to as universe breakers by the research team, challenge conventional theories, as they are already so large and luminous at such an early stage in the universe's development. The discovery of these galaxies raises intriguing questions about the rapid evolution of the early universe and challenges existing models of galaxy development. Traditional theories propose that galaxies form gradually over billions of years through the merging of smaller systems and the accumulation of gas and stars. The presence of these enormous galaxies so soon after the Big Bang suggests a more complex and potentially faster process of galaxy evolution than previously believed. Additionally, This discovery highlights the critical role that technological advancements play in transforming our understanding of the universe. The JWST's ability to peer deeper into space and capture faint light from distant galaxies has provided cosmologists with valuable new insights into the early stages of galaxy development. These discoveries have broad implications for cosmology, prompting researchers to reevaluate and refine existing models to better explain the complexity and variety of galaxies observed across vast timescales. These findings underscore the dynamic nature of scientific knowledge, where new discoveries can trigger breakthroughs and open new avenues for research. As scientists continue to analyze data from the JWST and other observatories, the study of galaxy formation remains an evolving field. Each new discovery brings us closer to understanding the fundamental processes that shape the universe and the cosmos as we know it today. As our understanding of galaxy formation advances, we are uncovering deeper insights into the processes that shaped the universe. The study of the early universe is no longer limited to theoretical models or distant projections. It has become a dynamic research field driven by cutting-edge technology. The James Webb Space Telescope, with its unrivaled ability to capture data from the farthest reaches of space, is enabling scientists to revisit well-established theories and explore new areas of inquiry. The recently discovered revelations made by the JWST challenge our understanding of how galaxies formed and how quickly they might have evolved after the Big Bang. These massive galaxies, dubbed universe breakers, are larger, more evolved, and brighter than previously imagined at such an early stage in the universe's history. As scientists study these galaxies, they are forced to reconsider the mechanisms behind galaxy evolution and how quickly these processes may have occurred in the early universe. The implications of these discoveries extend far beyond cosmology, with the potential to reshape our understanding of the universe's development as a whole. The discussion surrounding these revelations highlights the inherent uncertainty within scientific inquiry. Despite the groundbreaking nature of the JWST's discoveries, many questions remain unanswered. Science must grapple with the possibility that traditional models of galaxy formation and evolution may need to be completely rethought. The new data forces us to confront uncomfortable questions about the timeline of the universe's development and whether our previous assumptions about galaxy formation and evolution were based on incomplete or flawed models. As we move forward, it is important to recognize that science is a constantly evolving field, always open to new ideas and possibilities. The JWST discoveries serve as a reminder that the academic community must remain flexible, willing to challenge long-held beliefs and adapt to new evidence. Scientific progress is driven by the willingness to revise outdated theories in light of new data. The revelations made by the JWST exemplify how a single discovery can prompt a reassessment of the fundamental principles of our understanding. One of the most exciting aspects of the JWST discoveries is the potential for future breakthroughs in how we understand the very structure of the universe. The telescope's ability to peer deeper into space and capture light from galaxies billions of light years away has opened up new opportunities to study the universe's earliest moments more meticulously than ever before. The data acquired from this research will help scientists refine their models of galaxy formation, explore the role of dark matter and dark energy in shaping the universe, and gain deeper insights into the forces that govern the universe's evolution. At the same time, these discoveries emphasize the need for collaboration between researchers across various fields. Cosmologists, astrophysicists, and scientists from different disciplines must work together to interpret the data provided by the JWST and ensure that these discoveries are integrated into our broader understanding of the universe. The complexity of the universe demands a multidisciplinary approach, and the JWST discoveries are a perfect example of how scientific collaboration can lead to significant breakthroughs in our comprehension of the cosmos. As scientists continue to analyze data from the JWST, they are also refining the tools and methods used to measure and interpret cosmic phenomena. The precision required to study galaxies that formed billions of years ago is immense, and each new discovery forces researchers to improve their techniques and update their models. This continuous process of refinement ensures that science remains a rigorous and self-correcting field, where new revelations lead to the advancement of our collective understanding. As we continue to explore the universe, the discovery of these massive galaxies will undoubtedly lead to new questions and hypotheses that will guide future research. Will the discovery of these universe breakers change the way we think about galaxy formation, or even the